Then overhearing is also to be avoided. You unnecessarily hearing somebody are not supposed to, that kind of things. Then energy outspending. When it lacks definition of transmission reception power level according to the various topology in particular application area, then that matters actually. Now, over emitting, that is means transmitting packets when destination is not ready. So it is wastage of energy, both radio energy and communication energy over the layers. Then control packet overhead. Sometimes you send data with additional overhead. If it is encryption, that's understandable. But sometimes with or without that also you send unnecessary things, not necessary to do that. You are not optimizing packaging the information to pass from end to end. Okay? So that also energy inefficiency source. So we'll skip actually the category of MAC protocol. They are there, but you can read it leisurely. Let's go to last two slides of yeah. See, there are how many? There are 47 MAC protocols. Okay, they've been analyzed here. Now, unfortunate thing is not a single protocol is accepted as standard. Okay. Yeah, it will be ideal to cover this one before going to MQTT and co-op, but it's kind of all the way around. But that's okay. They take their points. So when you look MAC to be considered for IoT or MAC paradigm for IoT, or you want to, sometimes some people want to buy the idea of MAC or trying to change anything in the MAC to be accepted for IoT, then they should look into a few things. Like you may have to think about application perspective, that how the nodes have been set, how often they are sending information. Okay? So many applications, post-station traffic will be sparse. I think I told that before, okay, for the IoT, because there are less number of nodes and information or data being sent is more intermittent, unlike wireless network. Example is your smart home. Smart home, you have got in a certain area, the number of appliances you have is many. If you look at that, many appliances will be there. But these appliances send maybe once a day, sometime 2-3 times a day, week, those kind of things. Okay? So data is communication is very sparse, and density is also many. Because with home you have got 20 appliances is a lot in certain square feet area. Okay? Now, the characteristic of wireless LAN that you are asking actually, its counterparts is essentially different. They have more number of they have more data to go and less nodes to be there. Then there have been variation of this wireless LAN. You must have heard these things already. They are all very popularly discussed in regular network, in CSMA, CDMA, OFDMA. Okay. Now these protocols, all these protocols, they have a significant delay or latency, and that make it unsuitable for IoT. Okay. Now the question is, why endure a high overhead and large delay MAC protocol in an IoT network if we are going to send only a few packets that arrive intermittently to each device? That's a fair question. Why should you use MAC? Okay. Now, what is wrong with the existing wireless technology? I think we pretty much would talk that. This has been repeating the whole thing actually, nothing new here. Now, something has come off after that is to make an efficient MAC protocol for IoT, there are some changes is necessary in the core principle. We call that as potential solution is called a MEAT, is efficient MAC paradigm for IoT. What happens there? Each device with the data in its queue starts its transmission at a sufficient low power level and careful choose the data rate. So it's saying that be cautious, but definitely at a low power level. And due to low transmission power, data can be encoded across a long duration. We are not sending a lot of data, but you have to send the accurate data more reliable manner. The multiple source simultaneous transmission from large number of devices at low power, low rate, sent intermittently essentially consumes less energy. Okay, that's the basically the idea. It's nothing out of blue, but they said be conscious and they're calling that if you can do that, you can have a MEAT or MAC level or IoT. Okay. With that basic information, I thought that may be a little gap between what we did. So 20 minutes not bad to take care of that. Let us take into device discovery in IoT. An example, simple example, you must have seen, you have gone to mall, people come with a pamphlet and give you. Okay. So their purpose is they want to get more customer to their shop and they get more profit. Okay. Now, it's similar concept, but purpose could be different. Let's think about that purpose only. What if I don't have to go out, but I set my shop, in my shop I set my device such that the device can know another person with the phone is coming that way, exact what time, how long he will be there. I take opportunity of that particular time slot and send message directed to him or her, then he get this information, if he's interested he can come. So without going with pamphlets, and my job is done, publicizing my store into better business is done. So that's the idea we can call that as a e-booklet, automatically sent by sub-devices to customer devices, potential customer devices. It's possible that just like a block email, block message, you can say I don't want such message. Fair enough. Okay? Now this requires devices the shop owner have, find the customer's device efficiently, underline that, efficiently, because it's very time sensitive. Okay? But they're not going to stand and stay there ever, right? You should know and quickly do your job, get out. Now this is a simple neighbor discovery problem that needs a specific protocol called discovery protocol that we are going to discuss. What is device discover anyway in IoT? Why it is relevant to IoT? Besides do the shopping, okay? Device discovery is a problem of finding useful devices in order to accomplish a task. It's a pretty broad purpose. Finding useful devices to accomplish a task. We'll have some examples next slide. And it constitutes a major challenge for IoT. So device discovery is a major challenge for IoT now. Okay? Once device finds another with a desired characteristics and establish a negotiated communication, novel service can be generated through cooperation. This is the hope. Take some example here. Now you see each circle actually saying that similar objectives, all similar things. They're all using a tower, they take example of disaster management. Now, disaster management happen to some infrastructure. Could be earthquake, could be fire, something. So what they need? They need ambulance, they need fire truck, they need other volunteers. So if they know who are the potential collaborators, they can put the message quickly to them and get the help. Another example is, what is this thing? Remote health care, same thing. You need, suppose you are going somewhere feeling bad, health-wise, you want to find hospital, okay? Then smart appliances, what are they looking for then? What is commonness in smart appliances? Applications. One example is, I was giving another example before that their sensors are there. I want to collect data from that. So I am going around and collecting data. That way my battery life of the sensors are increased. Okay? Now, when I go, you know that typical IoT time of duty cycle of IoT time is essentially 4%, which means sensors sleep 96% time. Only 4% they awake. So that time you have to get the data. So what is probability that I can do that? If I discover that, okay, these are sensors near me, then I can easily talk and get it. That's another application over there, for smart applications things. Then you have got many other things like, say, light, it is what you call that, traffic light. Who are the collaborators? Vehicles, camera, okay. Now, these essentials, okay, suppose you want in future, you want actually a trafficless road, the road has no traffic. Then every car that coming around a cross intersection, they should look for the collaborators around that. They will discover who are my other people coming, are they danger to me or not. If I know their speed, if I know their position, then I can pass. Okay? So there are many potential scenarios where device discovery helps to enhance the technology, achieve modern technology to be built into the infrastructure. There are so many possibilities. I told you that your vision is to be big only, then you can think about. So there is something called opportunistic networking. So what is opportunistic networking? It defined like this. Opportunistic networking is a state that enables communication in IoTs. Okay? Enables communication in IoT. Otherwise, you don't need it, but when you need it, you go for that. Just like you have a friend, he always comes to borrow money from you when you need it. Other time, don't care about it. Okay? So it's opportunity. Same idea here that someone wants to network when he needs it, communicate with it. Otherwise, that's good. Sometimes it's not a friend example, but in reality, for communication, M to M is good. Where the scope of networking is possible and great, the devices are statics. But it is a little challenge for the mobile devices. Okay? Now, if it's possible, then new communication possibilities will be there. Now, without opportunistic routing path, disconnected networks of devices could not be connected to the internet world. So what it's saying here, now having opportunistic networking is good, but sometimes you would ensure that the network could be potentially connected when they are needed. Okay? And it is possible. It is possible to build a protocol around that. I'll show you actually a few things, examples will do that later. Yeah. The next is sensor network need neighbor discovered protocols. Okay. Say you have 1,000 sensor nodes deployed urban area for environment monitoring. For network diagnosis, the admin is carrying a handset, going around to collect the packets from sensor node directly. Okay. Now, because the reason that they are always sleeping is hard to get that. So we should have some kind of protocol, a strategy that they can say, hey, I am here, or I can say, I want you guys, wake up and give me something, those kind of things. So how to find neighbors from a network? Link layer discovery protocol is an open protocol that allows devices to discover and share information with other devices, okay? But not the servers. Okay? This is a typical protocol started with, but there are more to that. Now, node discovery protocols determines the pattern by which each radio turns on or off. Let's think about the first one. Let's call that node A. 6 means at the 6th clock, 1, 2, 3, 4, 5, 6 clock, it awakes. Then sleeps 5 clocks. Again 6 clock, awake. It repeats. Second one, node B, in 9 clock, it essentially in 9 clock unit, it awakes twice. First in 2nd clock, then in 9th clock. Then repeat. Clear? Okay. So the period in the first case is 6, that what is 6 means, period, repeating. Second case, period is 9, 2 means twice, repeating. So duty cycle, how about duty cycle here? The first one is 1/6, for second one it will be 2/9. Now, if you try to find out node A and node B, can they discover each other? To discover each other, they should be on same time, and sometimes there are two ways actually. One is if both are on same time, they can discover. That's called synchronous detection. The asynchronous detection will be one could be on or could be off. Okay. So it goes to second one. Look at this. When is going to find? At how many clock is it going to find it? It finds it, but after how many clocks? 18. Same thing, right? LCM stuff. Now, suppose there is a drift or shift. Okay, then what happens? They don't, right? They can't meet. They never meet. Okay? It's possible. So shifting is a problem. That means this will sync synchronously, no shift. But what you need actually, you need they should meet in spite of shifting. Okay? That's also a requirement, right? To guarantee that they are going to meet. So a viable neighborhood discovery protocol must either implement a clock synchronization or be robust in the face of clock shift. Is the requirement clear? Synchronous or even at clock shift, drifts.
But by the name actually it means that that particular node should not be visible for them.
Yeah, because they wake so rarely, and because of a drift, when they expect to happen, it didn't happen. If there's no drift, it could happen there. So when drift happens, it is not synchronized. So clock synchronization is good for that reason. Now, so what is the goal? We are defining problem now. Till now, an example of how they can discover each other, what scenario, what are the obstacles. Now you are basically setting a nice goal for that. What is the neighbor discovery protocol objective and challenges? Let's know that and try to find some solutions before you close. The goal is how to guarantee the discovery with a reasonable latency. That's very important. The first case, how many periods? 2 cycles, not 3 cycles, right? For A, it is 6 times 3 cycles. For second, it is 2 cycles, but that means it is 3 cycle or 2 cycle, the time is same, 18 clocks, and that is your latency. You don't expect to meet after 1,000, 2,000 clocks. Still is better, depending clock is megahertz, then still possible. Okay. Again, reduce at the same time when you try to make a less low latency, at the same time you don't want to do that at the cost of frequent awake. If you make frequent awake, sure you can get it quickly. So reduce wake slot to conserve energy. At the same time, latency of detection will be low. Then best efforts to match the existing duty cycle granularity of devices. What it means actually? Every device comes with certain duty cycle granularity. Okay? So what the best effort to match them? We did that. One example is basically LCM things. Now challenge energy constraints. Because of energy constraint, we can't meet. We can meet, but I don't prefer to do that. Okay? Then no network level time synchronization. Okay? Then duty cycle length is different for different devices. These are the challenges. Okay? So how can 2 neighbor nodes that not necessarily operate at the same duty cycle wake up infrequently and asynchronously discover each other without any prior coordination or knowledge of their energy conservation parameters, encounter patterns? That's the definition of the objective. So neighborhood detection protocol challenge is this statement. So we have this problem statement to solve. Before going to solution, let's classify the protocols. Okay? At a higher level, there could be direct and indirect approach. Direct approach, a node is discovered by a neighbor node only if the neighbor node directly hears from this node. Fair enough. Okay? How? Different thing, but this is direct things. Indirect is go through direct. Basically, direct is important. Okay. At a low level, the direct neighbor discover protocol are further classified into probabilistic and deterministic protocols. We'll discuss them. Okay. In probabilistic protocol, what happens? You adopt probabilistic strategies at each node. How? You find out how much time is active oversleeping with the different probabilities. The advantage of stationary network is good because this is fixed, but if it is moving, that's problem. But the drawback of that is it lacks discovery guarantee. Why? Because probabilistic, you can guarantee. Okay? Deterministic is good because it provides guarantee upper bound or worst case latency, how long it takes to discover. This slide will be giving example of a probabilistic protocol. Now, you consider a collision-prone slotted network with n nodes. A node remains in one of the following states, either transmit T, listen mode L and sleep mode S. Then you can define it. Node A is discoverable or is discovered by another node B in slot T if A is in state T, B is in state L, and no other node in state T. Does that make sense? One is sending, one is listening, okay, one is transmitting and listening, and others are not transmitting. Just saying that. There's a protocol called birthday protocol. Okay? The birthday protocol has three operational modes. What are they? The first one is, we call it birthday listen transmit or BLT, where node operates in state T with probability PT, and in state L with probability PL, and in state S with probability 1 minus PT minus PL. So the expected number of discovered link within the networks under this birthday listen transmit protocol in one slot will be this. This theorem actually, it is not, details are not given, it's just saying these things. Now the question, if you take this and try to find out the guarantees, will it be 1? If it's 1, then guarantees. Not guaranteed. Second one is birthday listen mode, where it aims at maximizing number of discovered links and never sleeps. So chance of discovery 1 by over n. It's better than that, but never sleeps is putting that into energy issues. Third one is combining this and this, sometime this, sometime that, till you find shorter durations. Now, if you look at deterministic approach example, consider two nodes A and B whose wake up schedule are 0, 0, 1, period 3, right? Just like we did before. 0, 0, 1, for B 0, 0, 0, 1. That means TA is transmit period is 3, for B it is 4. Transmit period of A is 3, B is 4. The duty cycle length of A and B are 3 and 4. So wake up schedule will be 12 slots, similar to what we did actually before. That was deterministic anyway. Now we can see that A and B can discover each other in slot 12. Now we'll look into some protocols actually, probabilistic protocols, exploits the birthday paradox, non-deterministic, no upper bound on discovery latency. Okay. Basically, its probability is basically non-deterministic. Then there's a protocol called quorum-based protocol, quorum. The quorum-based protocol will basically go into detail on that, explains the geometry of 2D array, and we'll talk about co-primality based protocol, which uses Chinese remainder theorem, that is for signal processing. You must have seen that. Okay, let's see how much we can handle today. Quorum never discover protocol. Now you have two, see, let me go back. We have period 16. So it is, you have to bring them to 2D. So the way you do that is, okay, so arrange the time slot into matrix formation. Then choose one row and one column as on slots, like this. Okay? Then the period is 16, but now you arrange it in matrix form, then creating one row, one column intersection like that. And this, why are you doing this thing? I'm doing this to ensure that nodes operating on same duty cycle, assuming that nodes are homogeneous, okay, they will discover each other within bounded time. That's the goal. See, now unfolding that. Okay. Then when unfold, we see something here in the period 16. How many times is there awake? So many times. 7 times? How many times? 6, 7 times. So your duty cycle is now 7 by 16. Okay? Now, so what basically, I didn't get any conclusion. So duty cycle 7 by 16 means you are in such a way that they are guaranteed to meet. The second one called co-prime neighborhood protocol is such like this thing. A co-priority based neighbor discovery protocol guarantees discovery for any 2 nodes for any amount of clock drift. That was trouble before, right? Any amount of clock drift. If the associated integer sets of node in this network satisfy the co-prime pair property. So key idea is co-prime pair property with worst case discover delay bounded by the product of 2 smallest co-prime numbers, 1 from each set. How? Example from theorem is 2 nodes with wake up schedule 3 and 2. Is that okay? A once in 3 cycles, the one is once in 2 cycles. Okay? Repeating, right? See that repetition? 1 0 0 1 0 0 1 0 1 0 1 0 1 0. So this is actually period. This is another period for A for this for 3. So the schedule 3 and 2. Okay. Now you time divided by 1 time slot. The B is moved by 1 time slot. What happens? Okay. Then, so in reality, each node choose 2 different numbers and combine their wake up slots. This solves the problem of 2 nodes choosing the same number. Okay, that's a trivial solution for that. Now, latest development in Disco, another choosing the prime numbers. I don't think I have included that here. Now, the performance parameter for neighbor discover protocol is discover delay, latency, granularity in duty cycle. That is, a neighbor discover protocol needs to provide sufficient fine granularity support to enable sufficient level of energy consumptions. This is basically balancing that. So granularity means what? How many times they will be awake up or sleeping. With more ones means poor. The granularity become high, low. Okay. Then robustness against clock drift. That's also another performance. How many? Sometimes, okay, my scheme, suppose you tomorrow design an algorithm for the node discovery. We can say, okay, I design a scheme which can tolerate 2 clock drifts, shifts. If the clock shifted by 2, sorry, if the clock is moving back by 2 or drift by 2 clocks, then it can manage. So more number of clocks shift it tolerates, it meets, is more robust. Now discovery diversity means in multi-channel network, it is desirable that a neighbor discovery protocol can achieve discovery on several channels to minimize the probability of neighbor discovery. By the way, this is a new area. It has a lot of research opportunities, by the way. Okay. Yeah, the lectures that we will cover after this, I can point out where the research problems are there. Okay. Now, deterministic heterogeneous node discovery problem. The statement goes like this. The problem is about devising neighbor discovery schedule for network nodes to limit or minimize the worst case discovery delay between 2 neighbor nodes, regardless of their duty cycle pattern and their relative clock shift. It's pretty hard requirement. Okay? Read again. The problem is about devising neighbor discovery algorithm or schedule, whatever you call it, for network nodes to limit or minimize the latency or worst case delay between any two neighboring nodes when they want to discover each other, even if their duty cycle pattern is different and the clock set could be any. There is one solution using quorum-based approach, where each node configures its neighbor discovery schedule based on a quorum. We'll discuss that. This pattern ensures that any two nodes have at least an active slot overlapping with each other regardless of time difference. We have two, one cyclic and grid quorum systems. Let's take each of them example and show that. Let's take the first one is actually cyclic, second one is grid systems. We have got two nodes A and B, and they have got 7 slots. You see those gray areas, okay, awake, sleep kind of things for A and B. So cyclic example, figure 2 left, this one is a upper one is actually say 1, 2, 3, 4, 5, 6, 7. Okay, then you find two quorums, A equal to 1, 2, 4. See, 1, 2, 4. Second one will be 3, 4, 6. Okay, 3, 4, 6. Now, what it says actually is called cyclic example. 1, 2, 4, and 3, 4, 6. Okay. The quorum is essentially for A is 1, 2, 4 when they are on and when this is on. Now, we'll see how it's working actually, but later. Now, the cyclic is coming again same definition actually over there. Now, for a grid, the two passes, see this and this. 1, 2, 3, 4. They're all 16 cycles and 16 clocks. Then they have been distributed like this: row, column, or row, column. So grid quorum system, two quorums, 1, 2, 3, 4, 5, 9, 13, 1, 2, 3, 4, 5, 9, 13. So quorum means the arrangement by which these slots are on. Okay. Now, let's solve it. Cyclic quorum based ND, node A is showing all that 1, 2, 3, 4 for the cycle. So 7, 8, 9. No, let's go back. We didn't remember that. Up to 7, right? 7. So typically 1, 2, 3, 4, 5, 6, 7. Then it again repeats. See, 1, 8, 9. So 1 to 7 is repeated and continuously cyclically going on. For node B, same way, repeating. Then, so typically whatever you see here, this is been in a cyclic manner in the following diagram. Now, if node B is moving, okay, then you will find that, wait a minute, okay. Now, in figure 3 what is saying, the neighbor discovery process using cyclic quorum in figure 2, that's the previous page, A, B can discover each other in slot 4, 11 if clocks are synchronized, or 6 clocks are unsynchronized. Okay, 4, 11, look at 4, then 11 for synchronized and 6 unsynchronized. Okay. When they're not shifting, okay, they don't shift though. Without shifting, you can possible cyclic quorum can discover two possibilities. Now, when they shift by 2 o'clock, for example, okay, then you can see, is there anything? Yeah, only once, right? Here. So, what happens actually, more they synchronize, more they meet in this process, and with shifting, and that's likely that even if not the 3 times, they will be meeting 1 or 2 times. Okay. Now, grid quorum is a example that how the neighbor discovery process using the grid quorum. Now, 3, 9, the second example actually saying 3, 9 when synchronous, and 5, 9, 13. 5, 9 twice. It should be 5 and 13, right? Maybe, wait a minute. Oh, okay, I got it. Now, here 3, 5, then 9, not 9, no, 3, wait a minute. Here it is 3, 5, 9, right? 3, then 3, 9, sorry, 3 and 9 here, but here you have got 5, 3 here, the 5, then you got 9 with reference to A. Oh, that's what confusing, with reference to A actually. Otherwise it can confusing. So 5, 9, then 13. Yeah. Okay. They are actually meeting that. So this allows even up to 2 shifts. So what you can all try to see if you want shift, how many are. So at least we want with reasonable delay, they could be able to meet. Okay. Now, requirement of neighbor discovery algorithm for IoT devices. There are low latency requirement that we have been telling it, and it is possible you can predict it using probabilistic approach, or we can learn it using deterministic technique, using quorum technique. We can provide a formula to predict it. Okay. Now, you can implement, what to implement device discovery. Can you implement on device itself, or it can be implemented actually at the midway, what do you call that, gateways, or it could be implemented more centrally. So device discovery that is implementing more centrally is essentially at the access point or base station. Okay. If distributed, typically is on device itself. Okay. So a complete discovery architecture must comprise of both centralized and distributed to ensure that something should happen with the reasonable latency and not to make the device awake frequently to conserve energy. With 5G technology, apparently it is being better. Okay. Now, you can use a device level and target device level, both means both A and B. If you want to source and target, both device level or base stations. In 5G systems, it can have also cloud that can also help as a central entity to provide the tracking and can say where the status of the devices to be. And sometimes still this area is so nascent that a lot of work is in demand. I believe with the sacrificing small energy, discovery can be possible. So everything has a cost. We cannot expect you want to discover and not no cost. So new technique, new algorithm could be coming up in the future. By spending some energy, see, you think about base station, server. They don't sensitive to the energy as the nodes. So you may have a part of implementation on the device and part in base station where they can use energy with the limited communication, they can try to discover each other. Okay? A server can gather different areas related to data and estimate the objective area. Then client uses the objective and transmit to discover request, and the help of base station, they can use the they can find the target. So this is actually the architecture, divide discovery architecture. It has got 3 sections. One is actually called RAN. See, all these cells are there. Then another is actually virtual node called eCloud, like gateway here. Then there is a control cloud over here. Okay. Now, whatever we discussed there, we only discussing few things for node to node at node level. But if you want to take help of servers or cloud or base stations, you can take help of a virtual architecture here, or even at the periphery like this. You call it actually control cloud or core network, whatever you call it. So RAN essentially consists of multiple radio access technology. Okay, see these areas, all of this, they're all everywhere. Then inside you have got your eCloud, then all of them talking to your central cloud or control cloud. So eCloud and CL, this and this, they constitute network function virtualizations, whereas this is actually physical domains. So in conclusion, the MAC for IoT is still evolving and yet to get standardization. So large body of wireless sensor networks protocols, they provide some insight to their use for IoT paradigm, and depends on matching applications they are successful or not, okay, or how efficient they are in terms of energy consumptions. And we discussed one potential future protocol called EMIT, okay, and some theoretical promise has been done by simulators using simulations intuitively, but we are yet to see the real implementation. Then, as regards to device discovery, more studies is needed. Now, what happens when clocks are different? We didn't discuss that example, didn't discuss that. Then direct and indirect discovery in more details, which has been left as an open-ended problem in the slide, did not tell how. Now, combining probability, deterministic approach, hybrid approach, these are all new research possibilities. People can do research in any one of them can get the PhD thesis. The fine granularities supporting duty cycles, and what happens with all that discussion we saw in discovery is static. Nothing has been done in mobility. That's another area of investigation. Okay, that's all today. So tomorrow we'll have AIoT, basically AI on IoT first. The second one will talk about cognitive IoT. That's the plan tomorrow. Then following day we'll do multimodal IoT. Then we go for data analytics in IoT, how they can do it. Now we have one lecture actually called fog computing for IoT. That is not accommodated, no, it could not be accommodated, but what we can do on Thursday afternoon as tutorial, we can do that. Fog computing for IoT. And the last day on Friday, we have two things, how the LLM is useful for IoT, okay. I think that's my student who's working in that area, she is going to present it remotely. Then from the lab, then we'll end with the security and privacy for IoT. That's the tentative plan, and adjusting many things here and there. Anyway, questions? So this is a lot of open areas. Lot of stuff to do research in this area though, okay?
You were mentioning that and then we'll discuss the areas where we can work on for research in this.
This is what, these are all there, yeah. Yeah, the most topics we'll talk, the new topics we're talking from now, I'll just point for the research areas are there. Well, till now we're talking some stuff, there are also research there, people are doing research, but I did bunch of things in the wireless sensor network. mobile sync, all those things many years back. So I don't have any interest in those areas, and more research focuses towards analytics area, cognitive area. Okay. So I would rather encourage doing research in new areas than going back. Okay. Not that people will not do that. Okay. This is up to them. Any particular question?
Identification,
Hmm?
time and calendar
Ta-
pick up to identify the devices.
Mhm.
Time calendar based engineering.
Time, calendar, the
Have fixed calendar, right?
okay,
Time and calendar is all the devices will be functioning with respect to time.
right.
Is that criteria can you pick up by using that?
It's possible, but it may be taking very long time. The latency could be very large. We do not know. So somebody has to do that research and find out. Yeah, because if you know those that when they are sleeping, when they are awake is known, and particularly if you have multiple channel, the question is you can find out which channel I can meet him. It's possible also. Yeah, that's actually the slides I skipped. It has been shown something there already. Yes, right. Those 7 slides I skipped. They are typical for the Mac ideas. They have used beacon there.
So all these things are there is a contention-free method. If you go with a contention method, we can with any one coordinator they can synchronize with all the nodes.
Yeah. So discovery is essentially we defined that earlier in the beginning of this that somebody is transmitting, somebody is listening. A and B want to meet and talk. Suppose I want to get in the attention of a B. I mean A attention of a B, then is transmitting or B is listening and transmitting. That and nobody else is doing that. So that's hard. I have only percent says that 40% things can happen. This is the challenge. If I import person to 5%, of meeting is okay. And we are still meeting, but because few areas, the applications, and they are independent systems. Do not have the house is earthquake or could be there. It has a nearby some device there. He's trying to use commands. That's not guarantee the is using is same as this ambulance is using or fire truck is using. There are a lot of uncertainty still there. Possibly there could be a different mode, and the one is showing a source signal can go to that discover mode and send a source signal, and others are bound to whenever the archive they give priority listening this. There are many possibilities there, still resources needed to be done. Okay. So everything is up in the air. Okay, you have to grab it. Thank you very much. Okay.